complex it is, how complicated it is to edit. Mentioned the cosmological constant, the ability to add up one extra term plus lambda g mu nu without affecting local conservation of energy. Then we said, okay, our goal from here on is to get solutions to this equation. And because it is so difficult to solve, because it's not linear, meaning that if we happen to know a solution, two solutions, any linear combination of them is not a solution. We must rely on some clever mathematical methods to introduce the concept of isometry. Is a mapping from the manifold to itself, which conserves the symmetry. And we show that there are vectors which are called Killing vectors, which are generators of the isometries. So K mu, Killing vectors. Satisfies Killing equation. K mu plus K mu is equal to 0. And if a vector K satisfies this equation, that means that K mu P nu is conserved along the geodesic. If K nu satisfies Killing equation, that means that K nu P nu is conserved along a geodesic set by the direction Q. This is something which we're going to make use of today, actually. And then we said, okay, let's try to find a solution to Einstein's equation. And we started to derive the solution. So we said, basically, we will derive in this course semester two solutions. There is a third one, which is a perturbation of gravitational wave that just looked at how many vectors we left. We really have time to fully derive it. I may or may not mention it depending on how much time we have. But in any case, at the end of the semester, you will be in a position that you can open the text and read it yourself and understand it quite easily. So I'm not too worried about that. We said we'll derive two solutions. One is the Schwarzschild solution in empty space. Well, of course, except for the trivial solution. Minkowski is a solution, 0 is equal to 0. Solution to Einstein's equation. We want a solution which is not a trivial solution. Started to describe the Schwarzschild solution. Schwarz. Solution. And we started by some general requirement, which is solution which is static and isotropic. We look for a static and isotropic solution. And again, I emphasize when we say solution, what we mean is a metric G mu nu that will solve Einstein's equation. And then we started to discuss some general properties of a metric which is static and isotropic without even making any attempt of solving Einstein's equation so far. And we realized that the metric, let me stop by saying that this general metric should take the form that ds squared, so general form of such a metric is that ds squared is minus e over 2 alpha which is a function of time radius, dt squared plus e to the power of 2 beta, which is another function of time and radius, times the r squared plus r squared d omega squared. Of course, d omega squared is d theta squared plus sin squared theta. And we got that by general considerations. Again, for metric, we did not even make any attempt at solving Einstein's equation. We just asked what would be the most general solution which represents metric which is static and isotropic. That's what we asked. And that's where we stopped before we went on the holiday. Any questions about any of that? No? Okay. So we continue our derivation of the Schwarzschild solution, and now we don't really have any more alternative. If we want to solve Einstein's equation, we just have to take this general form and plug it into Einstein's equation, which, as you can imagine, is not such a nice task. Especially not for Schwarzschild, because he did not have any computers that would do it for him. So actually he did it by hand, but then again, we have plenty of time. And as a matter of fact, it's one of those tasks which is annoying but not difficult. It just you have the metric, calculate the inverse, calculate the finite energy. So when you do this, and if I'm switching t, r, theta, phi, just write it as 0, 1, 2, 3. One ends up that the only non-zero components of the Christoffel symbol, non-zero component of the Christoffel symbol is look like that. Gamma 0, 0, 0 is E0 alpha, gamma 0, 0, 1 is E1 alpha. Gamma 0, 1, 1 is e to the power 2 beta minus alpha, and b0 beta. Gamma 1, 0, 0 is e to the power 2 alpha minus beta, d1 alpha. Gamma 1, 0, 1 is 0 beta. Gamma 1, 1 is d1 beta. Gamma 2, 1, 2 is 1 r. Gamma 1, 2, 2 is minus r e to the power minus 2 beta. Gamma 2, 1, 3 is 1 r. Gamma 1, 3, 3 is minus r e minus 2 beta sin squared theta. Gamma 2, 3, 3 is minus sin theta. No sin theta. Just erase that. And gamma 3, 2, 3 is minus. Okay, go and check. And everything else is either 0 or symmetrical. Once we have that, then the next step is to take that and calculate the Riemann. So the Riemann tensor again, only non-zero components and other components which you can get from properties of the Riemann are 0, 1, 0, 1 is e to the power 2 beta minus alpha. E0 squared beta minus plus E0 beta squared minus D0 alpha, D0 beta plus D1 alpha and D1 beta minus D1 alpha squared minus D1 alpha squared. R0202 is minus R e to the power minus 2 beta V1 alpha R0303 is minus R e minus 2 beta sine squared theta V1 alpha R0212 is minus R e minus 2 alpha V0 beta R0313 is minus R e minus 2 alpha sine squared theta V0 beta R1212 is R e minus 2 beta beta R1313 is R e minus 2 beta sine squared theta V1 beta and R2323 is 1 minus e minus 2 beta sine squared theta. Okay, like this, that's what you get. Everything else is of course either 0 or obtained from these ones by the symmetry properties of the Riemann tensor. Nothing to do. Take a contraction and get the Ricci tensor. So it's like in here. I guess nobody will totally objectify and just erase what was here. There we go. So this one. And again, I welcome you as an exercise to go just plug in. And what we got is R00 is D0 squared beta plus D0 beta squared minus D0 alpha D0 beta plus e to the power 2 alpha minus beta d1 alpha squared minus d1 alpha squared minus d1 alpha d1 beta plus 2 of r d1 r11 is minus d1 squared alpha plus d1 alpha squared minus d1 alpha d1 beta minus 2r d1 beta plus e to the power 2 beta minus alpha d0 squared beta minus plus d0 beta squared minus d0 alpha R01 is 2 over R is beta. R22 is e to the minus 2 beta. R e beta minus alpha minus 1 plus 1. And R23 is R22 times sine squared. Okay, fine. So just algebra. One can easily get lost, but there's nothing conceptually difficult. Yeah, just took metric, and we just plug it here. And now what we're going to do is to solve Einstein's equation in vacuum.
Did you contract the Riemann tensor with the metric 1, 1?
Sure about it, yeah. To get the Ricci,
one upper,
to get the
one
Ricci,
lower. Yes.
to get the Ricci, I do the construction for the Riemann tensor.
Yes,
The
but
standard way.
it's not metric like both upper or both lower indices. It's one upper, one lower, right?
No. This is the Riemann tensor, right? It's a 1-3 tensor. This is the Ricci tensor, which is a 0 to tensor. I'm not changing anything. It's the same thing we learned previous weeks. To get the Ricci tensor from the Riemann tensor, we made a contraction of the first and third. Right? Contraction includes summation. Remember that? R mu is R mu, sorry, R rho mu C. Yeah. Just follow exactly what I taught. It wasn't lying, it wasn't cheating. Exactly the same thing. I'm just using it right now. Yeah. Okay, now we said, let me okay, can you erase that? Okay. So we look for solution to Einstein's equation in vacuum. What does it mean in vacuum? Einstein equation in vacuum. What does it mean in vacuum?
All of the components of stress and intensity.
Yes, d mu nu is equal to 0. There is no matter. So that means what? Would I write Einstein's equation in that case?
Half mu is equal to half.
No. How do I get R? R mu nu. So we can simply write R mu nu is equal to 0. This is Einstein's equation in vacuum. Again, this is something which is confusing, so I want to emphasize that again. It does not mean, I mean, the way it's written basically is, okay, everything is 0, so it's a solution. Because 0 is equal to 0. There is another solution. So in a way, this is a solution outside of a gravitational tension. Sorry, outside of a gravitational source. So you can think of an astronaut that is orbiting Earth. Surrounding the astronaut is vacuum, but it's subject to the potential of the Earth. What we really do here, you'll see that, is really assuming that there is a delta function in space and time. Not in time, but in space. Delta function in space and R equal 0 when there is a source of matter.
So T00 should be a delta function, right?
At 0, 0, yes, but we'll see that.
Oh.
Right now we have R mu is equal to 0 for all mu's and u's. So this is to start with that. So R01 is equal to 0. So that already tells us that what does it tell us? Yeah. So this tells us that the 0 beta is equal to 0. Now we have R22 equal to 0. This is also equal to 0. So we can take the time derivative of that and use the fact that d0 beta is equal to 0. d0 of this equation basically. And plus the fact that d0 beta is equal to 0. And that means, that gives us that d0 v1 alpha is equal to 0. So what is written here basically is beta is not a function of time. Remember, alpha and beta are functions of time and radius. So this says that beta is not a function of time, but only a function of radius, so we can write it down. Beta is beta of R. And what that means, we can make a separation. Alpha is a function of time in R. We can write it as alpha is a function of R plus some function of time, which are separated.
Why plus?
What?
I mean,
The minus here.
can
Minus.
be,
G is a function. It didn't say what function it is.
but it can be multiplication.
No. Because then when I take the two derivatives, I won't get a 0. taking derivative with respect to r, and then derivative with respect to time.
But f and g, they are arbitrary functions. Right?
But they are only function of time in r, and only function of r.
Yes, but why you
Let's say
can
which
choose them this way? That's the multiplication of them also.
They're separate. This is a function of the coordinates, this is a function of the time. This gets different value in every equation.
It's like,
Think of it as I think you should have done that
it's
in
like
one of
maybe
your
from
math.
a, yeah, okay.
Possibly, yes. I don't remember where you saw that. I'm pretty sure it's now remember, alpha appears as the first term in the metric, right? We have the term that looks like minus e to the power 2 fr e to the power 2 g t squared. That was part of the metric. Minus e to the power 2 alpha. Now, but the choice of dt was arbitrary. It didn't specify what is the time coordinate. So I can simply take that, the time coordinate, and redefine it, basically, rescale it. Okay. Take dt and multiply it by e to the power g. Okay. Which means that the dt rescale. Dt go to e to the minus g of t, dt. Then gt is disappearing. Okay. This is a rescaling of t, which means that I can get rid of g of t.
Now every place you have a zero derivative changes, right?
Zero derivative with respect to time.
Yes, but now you're changing the value of t. So any place you have the zero should now change, right?
Yeah, but I don't care. Everything is equal to zero.
Okay.
What I showed basically is I can write the metric. So we can write the metric as ds squared is a minus e to the power 2 alpha of r dt squared plus e to the power 2 beta of r dr squared plus r squared d omega squared.
Why is the minus g? dt goes to e minus g.
I want to absorb this g e to the power
But
2.
this one doesn't have a minus.
But if I absorb that,
No, you use like exponential.
yeah, the beta.
Oh, so, oh, I see. Okay.
I want to absorb
Yeah,
this.
yeah, I got it.
Okay. So that I simply redefine the time coordinate.
Can you
Yeah,
write the Ricci tensor once before change? Now the Ricci tensor should change. Change the metric.
What do we mean should change? These are the components of the Ricci tensor.
Yeah, but
For that metric, these are the components of the Ricci tensor. The Ricci tensor just depends on alpha and beta,
Okay.
not on anything else. These are the coordinates. T is the coordinates. G is the metric.
But now, okay, now when you're writing d0, you mean the
D
new
zero,
the new t.
The new T. Yes.
Okay, okay.
It doesn't matter because they're going to get it zero anyway. It's just a rescaling, just stretching. I mean, think of it as working in centimeters versus meters.
Okay.
I did not specify what will be my coordinate. Just have what do we find? What can we tell now about the components of the metric? Static, right? They are independent on time, right? We said that killing vector, so that means that this metric possesses a time-like killing vector, right? So we write down. So any spherically symmetric we didn't make use of anything else. Any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay. So, any spherically symmetric vacuum metric possesses a time-like killing vector. Okay That's because none of the components of the metric depend on the time coordinate. Okay, just for you, so I had some discussion here. Just for you to know, this is called when we have a metric that does not depend on the coordinate or on the time-like Killing. Does not possess a time-like. Okay. When we have a metric that possesses a time-like Killing vector, the metric has a name. It's called a stationary metric. Stationary. Now the difference is a little bit confusing between what's called stationary and what we call static. Stationary is if you have a time-like Killing vector. Static, technical means that if the time-like Killing vector is orthogonal to a hypersurface. Where do you see that? In the stationary metric, the metric components themselves don't depend on some coordinate, but you could have a cross term, dt, dx term in principle. We don't see that here. Where we do see that, for example, when we have a rotating black hole, which we will not discuss here, then we have a situation of cross terms, which means that when you are going in one direction, then the time will also forces you to move on. This is the reason why you get in rotating black holes a region where you are forced to move to rotate with the black hole. It's called the ergosphere, which are things happen there. We will not discuss that in this course. If you want, you can play out more in depth. Let's first understand the situation. A more simple way of looking at that. Just for you to get a feeling. Static means that nothing is moving. Stationary, moving in a symmetric way. So for example, if you look at our solar system, right, we're all moving in a symmetric way. Right? So there is a difference between past and future. Right? If you look at something which is completely static, then it's not moving. I don't know how much more we'll have to go into these semantic things in this course, just for it. Okay, so this is for that. So we reached that. Now we still need to get alpha and beta. Didn't say what they are. We still have these two terms here. Both of them are equal to 0. So what we do now is take R00 and multiply it by e to the power 2 beta minus alpha, and add that to R11. So we have e to the power 2 beta minus alpha R00 plus R11, which is equal to 0. So as you can see, when I multiply them, most of these things here cancel out. E to the power 2 beta minus alpha, everything here basically will cancel out. This most thing will cancel out, and what we're left with is these two terms. Is 2 over r d1 alpha plus d1. So this is equal to 0. Which means what?
Should be the same.
No. d1 alpha plus d1 beta is equal to 0. Alpha is equal to minus beta plus constant. And again, the constant is something which is constant, so we don't need it. We can absorb it into the r, into t. We don't care, it's just a constant. So we can simply write down alpha 0, then this will give us e to the power 2 alpha. Now it will be 2r. B1 alpha plus 1 is equal 1. Hope I didn't confuse that. I switched that to the other side, so I'm actually going to switch that, so that's a plus 1. And this is the same as writing d1 r e to the power 2 alpha is equal to 1. This is an equation which we can solve. The solution would be e to the power 2 alpha is equal to 1 plus constant called mu over r. Mu is the constant. Overall, we get that. Write down ds squared is a minus 1 plus mu over r dt squared plus 1 plus mu over r minus 1, so that is minus alpha, dr squared plus r squared d omega squared. It's not bad. We only have one more thing to do, which is to get what is this constant mu. How do we get that? How do we get to get the constant mu? Sort of. Or, what do we call that?
Units, sure. Units.
That unit of r, we do.
Yeah.
We want to know what it is.
Some
Boundary conditions is what boundary conditions it be?
R goes to infinity.
R goes to infinity. So what happens to R goes to infinity?
It looks like Minkowski.
Well, it looks like Minkowski, yes, R goes to infinity, right? But we want something more than that. In fact, it looks like Minkowski called asymptotic flatness.
Yes.
But we want more than that. R goes to infinity, but not a 0. What should we get?
The delta function. The delta function.
R goes to infinity.
Yes.
What should we get? We're very far away from the source of gravity.
Slide space.
Asymptotic, yes. Slightly before that.
Newton.
Newton, right? What is the Newton?
G and
Said that we call it. How did we call it?
Wakefield.
Weak foot. Very good. So we want to get the weak field approximation. We want to get the weak field approximation. So we want to get the weak field approximation. So large R. And R goes to infinity. We get the weak field approximation. Internal limit. So we got G00, where R goes to infinity. Okay. Well, here it's simply is minus 1 plus mu over R. G11, that R goes to infinity is a what?
1 minus.
1 minus u over R. We should get minus 1 plus 2 phi. What is phi? What is phi?
Gravity potential.
Gravitational potential, right? Which means we're quite good. Quite good situation. So what is left is to write down mu is equal to 2gm. If we write this down, sorry, minus 2gm. Minus 2gm. Minus here. And overall, we finally get the Schwarzschild metric. Minus 1 dr squared plus r squared dr squared. That is the famous Schwarzschild metric, which again is a solution of Einstein's equation. In principle, M is just a parameter. It's a parameter which we happen to know is, it makes sense, physical sense, so we equate it to the mass of a simple object that produces the gravitational potential. What happens if the limit M goes to 0? Yes. Not surprising.
No mass, no curvature.
What? Sorry?
Well, I said no mass, no curvature.
No mass or curvature. And when R goes to infinity, what's we also go to no speed. We're very far away from the source of potential, so we don't really know about it. That's called asymptotic flatness. Now remember when last time I told you that there is a theorem which is called Kirchhoff's theorem, which we nearly proved it all because we went through all the steps except for one last step which I omitted, which states that the Schwarzschild metric is the only spherically symmetric solution to in vacuum to Einstein's equation. This is known as Kirchhoff's theorem. Metric is the only spherically symmetric solution to Einstein's equation. It's a uniqueness theory. Proof is basically following what we did, because we simply it's proof by construction, basically. Yeah, one last comment is we did not say anything about the source of the gravitational potential. So it could be a star that is collapsing. It doesn't have to, the source doesn't have to be symmetric at all. Right, now you see what I mean? I said you can think of it as being a delta function in space, but you can think of it as not being a delta function. If you're far away from it, you'll still see that solution. So this solution is the right solution for the metric in the solar system, or the metric outside the Earth. This is for the astronauts orbit Earth field, which is aligned with the idea that you can take all the mass of the Earth and put it in a single point in the center. This is not correct solution, for example, inside the sun. Right? So inside the sun, it's not a vacuum. There's gas anywhere, so you cannot use that solution. Outside the sun, it is the right solution. Right?
Even if it's not point.
Yes, that's what I said.
source.
Yes. So
Yes,
the vacuum is the vacuum is
potential is for only 2 points.
It will still be true as long as you're in, if you're surrounding in regions of vacuum and the point sources, the source is outside of regions. But
Like
basically similar to Gauss.
Yeah, but Gauss law for point vacuums, not for for sphere Gauss.
Okay. Let's take a moment now and have a look at the solution. After finishing your query, the solution. Other interesting points in the solution.
with the resonance.
But
It's a resonance.
there's no resonance. But what do we find?
If
Equals radius.
So
there is a rub when it's vanished.
there is a what? So interesting radii of the Schwarzschild solution. Right. What would be an interesting radii of the Schwarzschild solution? Interesting radii of Schwarzschild solution. But interesting is that something mathematically, at least from the solution, something interesting may happen. May, it doesn't have to happen. Do you find anything like that?
C squared.
That's right. Yeah, so the first one is, what did you say?
Equal to GMM.
G2gm over c squared. Obviously, when r is equal to g over c squared, we got the 0 here. We got the 0 here, r minus 1. So we cannot do it. This one. Is it the only one? Everything else looks good to you.
R equals 0.
Yes, of course, r equal to 0. We're
Also
dividing by r.
problem.
So 2, r equal to 0. Obviously, you cannot divide by 0. If you try to divide by 0, it will blow up. So something interesting might happen. Why do I say might happen?
Because it might not.
Because it might not. Why do I say that it's not obvious that anything interesting happens? Because it could be just an artifact of the coordinates that we chose. What do I mean by that? Let's say you have a flat space-time. Right? Just flat, two-dimensional flat space. I want to describe this space in polar coordinates. Right? So I will write it down, this space as dr squared plus r squared d theta squared. Right? So g, right, g mu nu would be 1 and r squared. Inverse of g mu nu would be 1 over r squared. So if I just look at that, I would imagine, right, something interesting must happen at r equal to 0. But is really something interesting happen at r equal to 0? No. This is just our choice of coordinates. If we were to select to choose other coordinates, like Cartesian coordinates, nothing special would happen at r equal to 0. So that's why I'm saying that the fact that we got with this mathematical prescription, we got something which looks fishy at r equal to 0 or at r equal to 2gm over c squared, does not necessarily mean that something interesting really happens there, because it could be an artifact of the selection of coordinates. So what do we do? Right, so G flat 2D space. What we got is G R R G theta squared. do we know if there's something interesting? So basically, I'm going to save you because this is a very long discussion that many mathematicians have debated upon for quite some time. Don't know exactly how long. So what we want is we look for coordinate free way of telling us whether something interesting happens. What do I mean by coordinate free?
Independent.
So what am I looking for? Some scalar. Scalar switch between coordinates and scalar doesn't change its values. Right? So we look for some scalar. So which is scalar itself obviously is not good because we give a 0. Right? So apparently there is another scalar, which has the great name of Kretschmann scalar. Scalar, which is K R U rho sigma R U rho sigma. Or conjecture that is that, and back to the scalar, follow its name, and you can simply plug in everything in the metric in the Riemann tensor, the inverse, or the indices, and you end up that R nu rho sigma R nu rho sigma is equal to 12 G squared M squared R R6. Which means what? What happens at R equal to GM over C squared? R equal to 0? There is so R equal to 0. Now, I have to be very, very careful. This is what I have to say. So we do it all the time. So R equal to 0 is a real singularity. Physics breaks down. We'll talk about that when we talk about black holes. R equal 2gm over c squared. It's nothing happens. Now it's in a way, which means basically the following: we could select a coordinate system which shows that nothing special happens. And we will do that. It's called coastal coordinates. So nothing happens. In the sense that we could select a coordinate system. And indeed, physically, of course, this is called the Schwarzschild radii, and this is the horizon for that. In reality, when I said nothing happens there, meaning that you can easily cross it. So if you're an astronaut and you, for any reason, want to enter a black hole, and it specifies it wants a black hole, it will be not today, it will be next week, most likely, or the week after that. You can easily do that. Nothing stops you from doing it. In fact, you'll likely not even feel anything when you do it. Of course, something does happen. What will happen is that you cannot go back in a way that black hole is the boundary of the universe. Once you enter, you can never go back. But you won't even feel that. Because really, nothing really happens there in some basic sense. You can simply cross it and that's it. You won't notice. We'll discuss it more thoroughly later on from somebody that looks at you from infinity. It will take you infinite amount of time to cross it. will happen there is some very tricky, nasty thing that the time will go to infinity. We'll see. But from your perspective as an astronaut, if for any reason you want to cross this radius, not only that there is no problem, you will not even feel anything special. Just keep on doing it. It's fine. Okay. So in the basic sense, really nothing happens. Now we said that there is something interesting, but we'll discuss it. So this has a name, first of all. This is called the Schwarzschild radius. This radius. Before we start, using fantasy about what may happen, I keep on telling you should be very, very careful in how you treat this radius, right? Because everything we're doing is relevant for fact. For example, a vacuum is outside of a star. So for example, if we take the sun, so sun, the mass of the sun, what if you happen to know?
10 to 26.
33.
33 grams. It's 2 times 33 grams. Next gram. That's enough. So 2 gm over c squared. Just plug the numbers, constants. Then you get that this is something like 3 times 10 to the 5 centimeters. 3 kilometers. This is the Schwarzschild radius of the sun. What is the actual radius of the sun?
More than that.
What?
Much
More
bigger.
than that.
Much. You know what is? How big it is? The radius of the sun?
20 kilometers.
To 20 kilometers. To the lower soul. It's 7 times 10 to the 10 centimeters. This is the radius of the sun. Right? Which is something like 5 times 10 to the 5 gm. So again, as long as we are outside of the sun, in vacuum, the solution is valid. So we will feel the metric behaves like that. But once we enter the sun, this is no longer a valid solution because there is no more. This equation is not valid anymore. So in reality, we don't need to worry about falling into a black hole or something. It's not going to happen.
You have other worries.
What?
You have other worries, so if you get close to the sun.
We get enough worries to worry about it. I need to worry about this. Obviously, there are objects of interest. Remember, we talked about it. There are objects in which all the mass is so condensed that the size of the objects are smaller than the Schwarzschild radius. Such objects, we know them. These are called black holes, and we'll discuss them. I promise you in the beginning. Not now. We'll take a few more lectures. Yes.
Can we use the Schwarzschild metric inside Schwarzschild radius?
Yes. You'll see why. Yes. In principle, what you need, this will be correct as long as the mass is enclosed in region, as long as you're in vacuum. Namely, that the mass enclosed is smaller than the sun is an example, and there is a mass of the sun, but it is distributed outside of the sun's Schwarzschild radius. That's true for pretty much all the objects that we observe, except for black holes. The masses of the black holes is enclosed inside the Schwarzschild radius. Okay?
But where is the threshold for black holes? For example, we cross the
The
radius.
Schwarzschild depends on the mass. Well, the larger the mass, right? It's still the point that the Schwarzschild radius is linear with the mass. mean, if you want, it's a critical density, which you pick up. You have a Schwarzschild radius. Every massive object has a Schwarzschild radius, right? Your Schwarzschild radius is very, very small. Your mass is enclosed outside. It's not impossible. It's not easy. So most objects that we know when we see stars, neutron stars, white dwarfs, whatever, they have masses. Simply they're distributed outside of their Schwarzschild radius. Except black holes.
But if we inside black hole, there is some energy distribution, right?
We'll get there.
That's why we can.
I'm not going to. I'll let you think about that for about 1 more week until we're going to discuss black holes. And everything will be clear. Right now, just use your imagination and think by yourself. Okay. Yes.
Is this when we imagine there are real system that behaves like that, but this is too simple. It's not rotating, it's not charged. It's like,
Again, that will take us.
I mean, the sun.
I knew that we started. I started using imagination. This is very fascinating. I won't really have time to discuss that. So I'll just mention there is what's called a no-Earth theory for a black hole. It says that black holes can be quantified by only 3 numbers, which is the mass, the charge, and the speed, internal and external. And there are solutions, known solutions to all these 3 metrics. Schwarzschild solution is a solution without rotation and without charge. For adding charge, it's called the Reisner-Nord Stream solution, which was found actually not very, very far after that. And if we add spin, this is called the Kerr solution, Kerr metric, which is reduced to the Schwarzschild solution in the specific case of spin zero. Now, there are very good reasons to believe by various works of scientists that in reality, if black holes are born charged, they will discharge right away, very quickly. So they may be born with some extra charge. There's no reason why, because the stars as we know them, all the material as we know it is neutral in the universe. Right? So if material collapses into a black hole, there is no reason to believe that only charged particles of one type, being electrons or protons, will collapse and the others will not. But even if that does happen, then what will happen is there will be a very strong potential, electric potential, that will very quickly attract all the charged particles from the surrounding, and the black hole will discharge pretty much immediately. So we don't expect to see any charged black hole. Rotating black holes we do expect to see, and we likely see. The metric is more complicated than that. Much more complicated, actually. It's very mathematical. It's quite messy, but there's no need to teach that in the first course in GR, because once you understand the concepts, it's something. I mean, the first thing, of course, is what they teach you is the concept. What does it mean, metric at all? It doesn't mean this is a metric solution in vacuum. Einstein's equation. These are all concepts which I believe we never encountered before. How do you solve Einstein's equation in vacuum with a rotation with a non-zero angular momentum? Basically, it's a mathematical challenge, but there is nothing conceptually that is different. Of course, the results are quite interesting, and there are various features which are put there which don't occur in Schwarzschild metric. But conceptually, it's not that intense. There's nothing conceptually new. I mean, in the solution there are new things. Before we go to discuss that, let's start by understanding the concepts, the new concepts here. I'm going to talk to you about ergospheres and other things that happen.
But when you are saying this describes well the solar system, it's because the sun rotates slow.
No, I say first, yes, you can think of that. I mean, I'm taking the approximation that the sun is not rotating. If the sun is rotating, then I need to make some corrections to this picture. But you're right that in reality the correction is going to be very slow. And what the takeaway message from me to you right now is that although the solution is correct in the solar system, correct in the solar neighborhood, we don't need to worry about getting close to the Schwarzschild radius because it does not really exist. Because if you want to get Schwarzschild radius, we need to enter the sun. And once you enter the sun, the solution is no longer valid. We need to look for a different solution. That's it. Okay. And of course, this is approximation. Approximate the solution. Okay. Any further questions for more?
Did Schwarzschild know how to distinguish between those two singularities? I mean, he wrote the metric, right?
He wrote the metric,
and I think he realized the problem.
it's obviously identified the radius, which bears his name, Schwarzschild radius. Whether he realized what's the true meaning of that, I'm not sure. Basically, you're asking me. I told you there was a long debate about whether this is a true singularity or not, and this debate lasted several years. I cannot tell you right away from my memory how long it took. You can easily check in Google, like Krechtmann, which year he introduced the scalar. I think it was a few years, definitely 3 years after Schwarzschild introduced his solution, and I suspect that Schwarzschild at that point was no longer alive. So I don't really know what Schwarzschild knew and did not know when he was dead. When he died.
And if, for example, we write the scalar for, let's say, 3D spherical coordinates, we also got.
I'm not sure to understand 3D spherical coordinates. It's not a question of coordinates; it's a question of metric.
Yeah, but we know the metric of spherical coordinates, right?
The metric is about that. You're getting confused with coordinates and the manifold space-time. I have a 2D. Okay, think of it the simplest way, right? 2D space can be flat, like this board, 2D flat space, and I can describe it in many different coordinates. I can describe this 2D flat space in Cartesian coordinate, in polar coordinates, whatever coordinates I choose. I can have a surface of a sphere, right? Like the surface of the Earth. Surface of the Earth is a different space than flat. We show they're not equivalent. Okay. I can also describe the surface of the sphere, which is also a 2D space in various coordinates as I wish. Right? It's my choice of coordinates.
So for 2D surface of sphere, if you calculate the scalar, we will not expect any problems, right?
I doubt if you get anything, because we said for the 2D surface of a sphere, you only have one number, which is the Ricci scalar. Right? Maybe one number, basically. But I don't know if definitely this is not a solution. But again, I get this is a solution of Einstein's equation. I mean, this is this metric. This metric describes the space. If you look very carefully at how this space looks like, then you know this. I'm pretty sure you've seen that picture, right? The picture looks something like that. If you're very far, it will be flat. If you get close to flat, something like that. Something that looks like that. Sort of picture.
Yeah.
The drawing from my side. This is flatter and flatter. There's like a. This is how the Schwarzschild looks like. Of course, 2D. Okay. And the Schwarzschild radius is basically this is the zero, like r equal to 0, 0, of course. This will be the Schwarzschild radius. So what really happens is you're moving in this space. We're going to discuss that's actually the next thing we're going to discuss, how trajectories look like in space. When you cross the Schwarzschild radius, Rs, right, then space is so curved that you cannot cross it back, basically. You can keep on moving the right direction. There's nothing prevents it. Spiraling. This is the picture you should have in mind.
Yeah.
That space.
It's valid.
What?
Is it valid picture?
Yeah, it's actually not a bad picture. Of course, it's a 2D, and because you cannot, in reality, what you have here is 4D. And so 3D is spatial, so I cannot put 3D right on the board. In that sense, it's very difficult to envision. The 2D is something much easier to envision. So sometimes you see this like toys that they do for kids, and you put a coin and then it rotates and spirals in. It's actually not a bad representation. Surprisingly, this is actually a visualization which is not that bad. What it would look like. Of course, it's in 3D, so it's very difficult to imagine that in 3D space. Okay.
What happens if the mass rotates? I mean, what part of the Einstein equation will change?
No, it will still be actually a question of vacuum. I will add some. There will be some extra terms to prevent
I mean,
rotation.
from what step they arrive?
I need to think a little about it. There will be some extra term that will show up. Where do we see that? Okay, I don't have an answer to it right away. I'll check it out and come back to you. Okay. Don't want to just say things. Well, okay. What questions about that? No. That's the part that things get more fascinating in this course. Now we're getting more to the physical part. Now we can think of, okay, could we get to that part without going through all the math first? I don't think so. But you can think for yourself if you have any suggestions for the future, if you think there's something which you could skip and still get to that. With that, please let me I can find it. You could skip and still get it. Okay, so the next thing we're going to do is to start looking at what happens to trajectories of particles in the Schwarzschild metric. And so this is the metric. Pretty much visualize it to you a little bit, the best I can do. And we said there are two interesting radii. We will get back to this radii. But we said currently in the close vicinity of what we do in the solar neighborhood, we don't really need to worry about them. Because everything we're going to do is going to be at radii which is much greater than the Schwarzschild radii. All the trajectories we can imagine in the solar system will be outside of the sun. Nothing will go into the sun. Even if they do, it's not a good solution. So right now, let's not worry about the Schwarzschild radius. We'll get almost there. But let us look at trajectories of test particles of this thing in the Schwarzschild metric. So motion of test particles. Of course, what do I mean by test particles? Yes, they are so small relative to other things that they don't affect the gravitation. But this can be anything. I mean, we can treat astronaut orbiting Earth does not affect the Earth's gravitational potential. Then we can say the same for the Moon. We can say the same for the Earth relative to the Sun. And the gravitational potential of the Earth is much smaller than the Sun. So I can easily ignore it when I look at the trajectory of the Earth as it orbits the Sun. Okay. Now, you've all seen Kepler's law, right? Because I had years of people did not, for some reason, see Kepler's laws. So we're going to redo them basically now, but GR version. So motion of test particles in Schwarzschild metric. So how do we solve the motion of test particles? Schwarzschild geodesic, Schwarzschild metric or geometry. So, okay, so we need to dirt our hands again. Write down the geodesic equation. That's going to be the obvious first attempt, and as we're going to see, it's not going to be this very far. So, of course, to do that, we need first to solve it, write down the Christoffel symbols of the metric. So, for the Schwarzschild metric. Yeah, gamma. Theta, gamma 233 is minus sin theta, cosine theta, and gamma 333 is a cotangent constant. Okay, straightforward. You just take the metric and you plug it in. Nothing special. And then we write down the geodesic equation. How many equations do we have? The geodesic equation? Four. Each for each of the 4 parameters. So let's write them down. So there's equations, 4 of them. So d squared t over d lambda squared. We have plus gamma, we have the gamma 0, 0, 1. So we should have plus 2 gm over r minus 2 gm dr d lambda d lambda is equal to 0. You all see where this comes from? The gamma 0, 0, 1, I have it twice because I have the r d lambda d lambda twice. Okay? So this is the for t. For the r, we have d squared r over d lambda squared plus gm over r cubed r minus 2 gm dt over lambda squared minus gm over r minus 2 gm dr over lambda squared is equal to 0. Oh, sorry, this is an extra line here. Minus r minus 2 gm, then d theta over d lambda squared plus sine squared theta d phi over d lambda squared is equal to 0, and then d squared theta over d lambda squared plus 2 over r d theta over d lambda d r over d lambda minus sine theta cosine theta d phi over d lambda squared is equal to 0, and then d squared phi over d lambda squared plus 2 over r d phi over d lambda d r over d lambda plus 2 times theta theta over the lambda phi over the lambda is equal to 0. First, go and check it. I'll cheat you here. Second, now we need to go and solve it. If we solve it, what do we get?
The trajectories.
Trajectory, geodesic. It does not look very promising. looks a little bit doable. I mean, modern less computers it's doable, but maybe not very illuminating.
Why we didn't choose the proper time as conversation and trajectory?
This is a general, I will do it also for photons. Okay, we will solve it for photons as well. But just choose a parameter along the trajectory. Could we choose a proper time in principle? Could you?
I mean,
If it's a massive particle,
for massive
yes.
particle, we
If it was a massive particle, we could choose a massless force. We may want to think for better. What's a better way?
better way to solve the
Yes.
equation.
To write down, or even to think of the problem. Yes. What do we look for?
Asymptotic.
Asymptotics. We want nowadays the question of motion, not just what happens.
Second law.
What?
Second law.
Second law.
Second law of Newton. No.
Don't need it. Come on. Spend nearly 2 hours. What? What do you want?
Symmetry.
What?
Symmetry.
Symmetries, thank you. Not symmetries.
Killing vector.
Killing vectors. Exactly. So let's look for symmetries, and killing vectors is going to be much more useful, I would say, and much more insightful. So that's what we're looking for. Solving it. How many killing vectors has it? How many killing vectors do you see?
That.
Which ones?
Just for
Case 4. Which ones?
more.
Which ones? Okay, not more. Which 4 killing vectors do you see?
Okay. Spherical symmetry.
We have
So
spherical
any
symmetry.
rotation.
Exactly. So we have
Theta,
rotations.
phi angles.
Right. So how many do we have for rotations? 2, 2, 1, 2.
Phi.
You can rotate around any axis.
So 3. It's
So we have 3,
Oh, okay.
3 associated with rotations. Right. So we have 3 rotations. Rotation symmetry. What else do we have?
Symmetry for transition in time.
Of time, yes. So one is in time. One static. Static. That's what we have. Now you may know, right? But killing vector associated with some time symmetry. What conserved physical quantity will be associated with energy? Energy. You've seen that, right?
Yes.
And if there is association with translational symmetry, momentum. And if it's rotational symmetry,
Angular.
you've seen that? Where?
Yeah. YouTube.
No, also in the analytical mechanics, quantum mechanics.
Okay, that's where you're supposed to see it. Sometimes, yeah, sometimes people don't see that, so it's very surprising when it does. Yes, so. Okay, good. So that's already give us some insight, right? Anyway, now we have the full mathematical wave, which I don't think that you've seen it before, because you did see killing vector. So each killing vector is associated constant of motion. Phi is associated with constant of motion. We showed it today in the recap, right? So if k mu is a killing vector, then we have that k mu dx mu over d lambda is a constant. So we certainly have, if we have 4 Killing vectors, meaning we have 4 conserved quantities which we can use. Of course, in physics we love conserved quantities. And in case you even know what they are. One is conservation of energy, two is conservation of angular momentum. Now there is another constant of motion which we can get, which is the metric compatibility along geodesic. Remember that? Plus metric compatibility along geodesic. That's epsilon is minus g mu dx mu over the lambda dx mu over the lambda. Equal to epsilon, because epsilon is equal to what? It can be 1 if it's a massive particle. It can be a 0 if it's a massless. Remember that? No? Go back, it appears in when we discussed that. It's a space like geodesic, it's a minus 1. Just think of that as
Can we measure this metric compatibility? It's very intuitive to think about energy on
no, this is the simplest way, you know, you can think of it as a g mu nu, u mu, u nu. Right, this is constant. Go back to even when we discussed that special relativity. U mu, u mu. Constant. So go back, we had not sure who was where did I put it? I think it was when we discussed vectors and tensors and Cohen spaces. When we first discussed geodesics. Go back, by the way, all the lecture notes, past lecture notes are online, so you can look at that. Obviously, go to the literature and find it. Okay, how am I doing this time? Okay. So let's start and see what we get done. I mean, our time runs out. We said we have 4 constants of motion, plus there is a metric compatibility, and that's what we will make use of instead of trying to solve directly the geodesic equations. Erase that for the moment. And we look at the angular momentum. So let's start with angular momentum. So this will be conservation of energy. This is conservation of angular momentum. Now we can think of that as either conservation of angular momentum around each axis. There is something which is easier to do, but angular momentum is a vector. Actually, it's a pseudo vector, but it's not relevant right now. And a vector, we can think of it as having what? What?
Components.
Yes, so components would mean, but we can think of it in a different way, of having a magnitude and direction, right? So the magnitude of the vector is one number basically. The direction we give by 2 numbers, right? So you can take these 2 numbers and specify them when these are constants of motion. Okay. So that means what? Simply means that the direction of the angular momentum of the trajectory of the particle is fixed. Which in other words means what? The particle is moving in a plane. Right? Think of the Earth orbiting the Sun. It's in a single plane. It's not, it can in principle orbit very well. The conservation of angular momentum means that we're always orbiting the sun in the same plane. It's exactly the same thing here. Right? So that is of course, if we have a particle which is in a different plane, we can simply rotate the coordinates and to put that in the equator. So this can be like 2 related to the direction, and 1 to the magnitude. Conservation of directions means that the rotation or orbit is in a plane. Orbit in a plane, which we call the equator. And again, we can simply rotate it. So in other words, we get that conservation of direction of angular momentum. We can simply write as theta is constant, and I write it as pi over 2. So all the rotation is in the equator. Okay, you're all with me? That of course means that the theta over the lambda is equal to 0. Already saves us. So we have, so these are 2 Killing vectors. Now we have 2 more. So one of them is associated with conservation of energy, and one conservation of the magnitude of the angular momentum. Conservation of energy. So this would be, we said it's a time-like Killing vector, right? So this is a time-like Killing vector. So how do I write a time-like Killing vector? Okay, you. What do I, when you say a time-like, what do I mean? It's only in the time direction. Only as a component in the time direction. Right, so you can simply write it as 1, 0, 0, 0. Right? Only as a component in the time direction.
But how do you know that this time direction is not dependent on lambda? It's some function from.
It has nothing to do with lambda. This is a vector. Lambda associated with the trajectory. I think maybe this is a good point for you to start reviewing the material, because by now I'm assuming that you know everything you've already learned. Now I'm making use of that to get trajectories of particles. So don't get confused. This is a vector. Okay. Lambda specifies a trajectory. I'm not talking about any trajectory right now. Okay. Just talking about the time-like Killing vector, which looks like that. So if it looks like that, talking about the conserved quantities. So k mu, what is k mu? I want to lower that. So if I want to lower k, right, remember I'm going to use that. So if I want to lower that, k mu is a g mu nu k mu. G mu nu is written here. So it means that k mu is just a k mu g mu. This is just a minus 1 minus 2 gm over 2 and then the conservation of energy. If I write it down, conservation of energy would be k mu dx mu over the lambda. Now comes the trajectory, right? X mu over the lambda. But k mu is just a 0 component. Everything else is 0. So x mu I can simply take the 0, which is time. So I can write that as there's a minus here, right? Because it's a minus. So I think I'll get 1 minus 2 gm over r dt over the lambda is a constant of motion. This constant, I call it E. But if it's a constant of motion, of course it will be associated with the energy. Okay? exactly the same rules that we wrote. D is a constant of motion. Now we have the magnitude of the angular momentum. Still left. So magnitude. So killing vector associated with the magnitude of angular momentum. L by the d phi, you can use the z direction because it's, if I said that the trajectory is in the equatorial, then angular momentum will be in the z direction. Right, so it's d phi. In other words, L mu is going to be 0, 0, 0, 1. So L mu is what? What is L mu? It's an R index, right? Be a what?
R squared sine theta squared.
0, 0,
Yeah.
0, R squared sine squared theta. Right. And since we said theta is equal to pi over 2, and sine squared theta is simply 1, I don't need that. Right. So what we get is R squared d phi over d lambda is equal to 1. Sorry, to constant, which I call L, which is the second constant of motion. So again, a constant of motion. Of course, this is total angular momentum. Which is again treated here as a constant of motion. Am I doing this time? Or the past time? So now it's a question of physical interpretation. I mean, what we did here is mathematically fully correct. Now we can think of we can talk either about massive particles or about massless particles. So if it's a massless particles, this would be really the energy and the angular momentum. You have to be careful associated with the trajectory of the particle. Right? So if we're talking about the photon, it doesn't mean that the photon will have that energy. The energy associated with the trajectory of the photon in this potential. And if it's a massive particle, you can think of these as energy and angular momentum per unit mass. Right. So by the use of these scaling vectors and the symmetries, we already we had these 4 lengths each of these equations. It took 4 coupled second order differential equations. It looks quite nasty to solve. We've already managed to make a big progress by reducing the amount of equations, essentially using the symmetries. It's a standard trick in physics. It's the same thing as instead of solving the Newtonian trajectory, just using conservation of energy, angular momentum. That's all. It's pretty animal. Whether we should do, I think this is a reasonably good time to stop here because now the rest is going to go and just develop that. It's actually not going to be very lengthy, so it'll take me another 10-15 minutes to do the derivation. So it may be, since we're over time, or you want to study for a few extra minutes. Don't care. Don't know if you don't care. It's good or bad if you're so excited or that you got no idea what to do. Okay, so we can do that on Sunday. Okay. So we're sort of in the middle of the derivation, but it's fine, we'll continue the derivation. Sunday and explore the trajectories of particles in the structure. lecture, so if I feel that we need more time, I have freedom to it. I don't know if we'll need. Depends on the interest of the crowd, how much time I have. Definitely the essential we cover, so there's no question. But now you see that the course is sort of switching gears, moving from more mathematical to now more physical description. There's still a lot of math. Maybe the connection to the physics gets more and more clear as we go on. This is a good time for you to review everything we did so far. As a result of having math, a lot of things that are very confusing, and you know, you don't want to do that in the last minute when you're really stressed before the exams and busy with other exams, etc. You want to do it now, there is still enough time, you can think more clearly, more relaxed, make sure that everything is clear in your mind, and you have time to ask questions and digest the answers. Don't wait until the last moment to get too stressed. That's my advice. You do what you want. I advise you to use the time now before the when we're still far enough from the end of the semester that you can make sure that you don't have any holes in your understanding. All right. Okay. So I'll see you on Sunday morning. Right. Good weekend.
Can I ask a question?